CS 3351 Digital Principles and Computer Organization. Topic is Counters, presented by Dev Salakshi, Assistant Professor of CSE Department, Rohini College of Engineering and Technology. Counters. Flip-flops can be connected together to perform counting operations. Such a group of flip-flops is a counter. The number of flip-flops used and the way in which they are connected determine the number of states and also specific sequence of states at the counter goes through during each complete cycle. Counters are classified into two broad categories. First one is the asynchronous counters and second one is the synchronous counters. So in asynchronous counters, the first flip-flop is clocked by the external clock pulse and each successive flip-flop is clocked by the output of the preceding flip-flop. In synchronous counters, the clock input is connected to all the flip-flops so that they are connected simultaneously. Within each of these two categories, counter are classified primarily by the type of sequence, the number of states or the number of flip-flops in the counter. The term synchronous refers to events that have a fixed time relationship with each other. 2-bit synchronous binary counter. In this counter, the clock signal is connected in parallel to clock input. So both the flip-flops, the output of flip-flop 0 is connected to J1 and K1, input of the second flip-flop 1. So here two flip-flops we are using. Here we are using the two JK flip-flops. Assume that the counter is initially in the binary 0 state, that both flip-flops are reset. When the positive edge of the first clock pulse is applied, flip-flop 0 will toggle because J0 equal to K0 equal to 1, whereas flip-flop 1 output will remain 0 because J1 equal to K1 equal to 0. After the first clock pulse, Q0 equal to 1 and Q1 equal to 0. When the leading edge of clock 2 occurs, flip-flop 0 will toggle and Q0 will go low. Since flip-flop 1 has a high on its J1 and K1 inputs at the triggering edge of its clock pulse, the flip-flop toggles and Q1 goes high. Thus, after clock 2, Q0 equal to 0 and Q1 is equal to 1. When the leading edge of clock 3 occurs, flip-flop 0 again toggles to the set state and flip-flop 1 remains set because it J1 and K1 flip-flops are both low. After this triggering edge, Q0 equal to 1 and Q1 equal to 1. Finally, at the leading edge of clock 4, Q0 and Q1 go low because they both have a toggle condition on their J1 and K1 inputs. The counter has now recycled to its original state, Q0 equal to Q1 equal to 0. 3-bit synchronous binary counter. A 3-bit synchronous binary counter is constructed with 3 JK flip-flops and an AND gate. The output of flip-flop 0 changes on each pulse as the counter progresses from its original state to its final state and then back to its original state. To produce this operation, flip-flop 0 must be held in the toggle mode by constant high on its J0 and K0 inputs. The output of flip-flop 1 goes to the opposite state following each time Q0 equal to 1. This change occurs at clock 2, clock 4, clock 6 and clock 8. The clock 8 pulse causes the counter to recycle. To produce this operation, Q0 is connected to the J1 and K1 inputs of flip-flop 1. When Q0 equal to 1 and a clock pulse occurs, flip-flop 1 is in the toggle mode and therefore changes state. When Q0 equal to 0, flip-flop is in the no change mode and remains in its present state. The output of flip-flop 2 changes the state both times. It is preceded by the unique condition in which both Q0 and Q1 are high. This condition is detected by the AND gate and applied to the J2 and K2 inputs of flip-flop 2. Whenever both outputs Q0 and Q1 equal to 1, the outputs of the AND gate makes the J2 and K2 equal to 1 and flip-flop 2 toggles on the following clock pulse Otherwise, the J2 and K2 inputs of flip-flop 2 are held low by the AND gate output. Flip-flop 2 does not change state. 4-bit synchronous binary counter. This particular counter is implemented with negative edge triggered flip-flops. The reason behind the J and K input control for the first 3 flip-flops is the same as previously discussed for the 3-bit counter. For the 4th stage, the flip-flop has to change the state when Q0, Q1, Q2 equal to 1. This condition is decoded by AND gate 2. 4-bit synchronous decade counter, that is BCD counter. BCD decade counter has a sequence of from 0000 to 1001. After 1001 state, it must be recycled back to 0 state. This counter requires 4 flip-flop and an OR logic shown below.